Euler angles started off, I don't know, I guess, seems like, yeah, I can handle this. But then as we get into it, we see that, wow, there are different interpretations, different possibilities for defining Euler angles. It's getting a little too complex for my tastes. Okay. So I'm going to show you a better way to do things. Okay. Now some might disagree, but I really think this is a better way. Okay. So a better 3-parameter representation for SO3. Okay. All right. So like anything, right? If you want to develop something better, okay, usually you need better tools. Okay, and to get here, we need some new tools. Okay, so I'm going to spend maybe the next 20 minutes or so reviewing some linear differential equations and then also generalizing that to sort of higher dimensional linear differential equations. Okay, okay. So first, some tools. Okay, so let's start off sort of gently. Okay. Okay, so this is something that I think most of you know the answer to. So suppose I give you this differential equation. Okay, where x is a function of time, scalar. Okay, alpha, also a scalar constant. Okay, and this dot means time derivative. Okay, so x dot of t simply means dx dt of t. Okay, and let's give some initial conditions. So let's say that x at say time 0 is some given x0. Okay, all right. So most of you being juniors and seniors, in theory, you're supposed to know the solution to this. Okay, in theory, okay, and I'm sure you knew, but something people forget, right? And life is actually an open book test. So important thing is to know where to look. Okay, so if you don't remember, just pull out your undergraduate differential equations book, or maybe even your high school math book. Okay, what's the answer? Okay, answer is the exponential, right, of alpha t times x at t0, which is given. Okay, so this is a solution. Okay, and I don't think I'm going to have many challenges to this. Okay, so that part we can agree on. Now what if I gave you this? Okay, and let me just, x is still a function of t, okay? But this time, x is a vector in dimension. Okay, and A is not a scalar, but now it's a matrix, n by n, constant. Okay, and we'll assume that x0 is given as the boundary condition. Okay, so x0 given. Okay, so now what's the solution here? What's the solution here? Okay, some of you know because you've maybe seen this in a controller systems class. All right. I'm going to pretend I don't know. Okay? I'm going to guess. All right, so what am I going to use as inspiration? I'm going to look at the scalar case, and I notice, well, it's the exponential of alpha times the initial condition. So maybe I can guess something like that. Okay, so x of t is e to the at times x0. Okay. Okay, so that's my first guess. Then the question is, what's this? Okay, exponential of a matrix. Okay, so what is that? So you say, well, okay, well, what is it in the case when it's a scalar? Okay, in the case when it's a scalar, you know, the easy answer would be just get your calculator, punch it in, and out comes a number. Okay, but actually, what that is, let's go back here. Okay, remember the definition. It's a series, 1 plus alpha t plus, right, alpha squared t squared over 2 factorial plus alpha cubed t cubed over 3 factorial plus so on. Okay, so it's an infinite series. Okay. Okay, so while I'm at it, I might as well continue. Okay, copy that, use that as a template. Okay, so I'm going to define the exponential of this matrix, A times t, to be, following that, I plus at plus a squared t squared over 2 factorial plus a cubed t cubed over 3 factorial plus, okay. So that's my guess. Okay, so now I have to ask some questions here. Okay, so the first question is, well, when I define a series, right, when you see a series, what's the first thing you have to ask yourself? Does it converge? Okay, does it blow up to infinity or does it converge? Okay, and we know that in the case of the exponential, it always converges. Okay, so here, does e to the at converge? And the answer is, so this is, we're not going to worry about the details, but they are available in standard differential equations textbooks. If A is constant and finite, yes. Okay, so for our purposes, A will always be constant. Okay, so yes, it does converge. So we're not going to worry about it blowing up. Okay, next question. Is my guess right? Okay. Is this a solution? Okay. A solution. Okay. So how do I check? How do I check? Well, easiest way to check is to just plug this back into the original equation. Okay. See if it works. So let's do that. So we have to calculate d dt. Okay, well, let's see. X dot. Okay. So that's the time derivative of what? I'm guessing this is my solution. Okay. So e to the at x0. Okay, I have to take the time derivative of this. Okay, how do I take the time derivative of this? Well, I have to use my definition. Okay, so let's go over here. So it's d dt of, all right, so I need to take the time derivative of something times something. Okay, something times something. So it's a scalar. So how do I do this? It's the derivative of this times this plus this times the derivative of this. Okay, that's standard, right, product rule. Okay, so it's d dt e to the at times x0 plus e to the at times d dt of x0. Okay, so x0 is given, it's constant. Okay, so it doesn't change with time. So that's 0. So we only need this. Okay. Okay, so we now take the time derivative of this series, e to the at, I plus at plus a square t square over 2 factorial plus dot 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 that. And I guess we need to do this times x0. Okay, so now we know how to take the derivative of this term by term. Okay, so this is d dt of I is 0. d dt of a times t is just a. Okay, this is a square times t plus a cubed t squared over 2 factorial. Okay, so there's a pattern here. Okay, so it looks like that. So you notice that there's an a everywhere. So I say, well, let's pull my a out, 1a. And then I'm left with I plus a t plus a squared t squared over 2 factorial plus dot 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 x0. Okay, and then I notice that what's inside the parentheses here is what? It's my original definition of the exponential. Okay, so this is a times e to the at x0, but then that was my solution, x of t. So this is a times x of t. So if we go backwards, a times x of t is equal to x dot. That's the original equation. So yes, so this works. Okay, so it checks. So it is a solution. Okay. Now, I say, wait. Over here, I pull the a out in the front. Okay. I could have pulled the a out to the back. Okay. Right, so this step here could also, I could have written as times a x0, okay, which is e to the at times a times x0. Okay. Is this a problem? Not really, not really. In fact, we've learned something interesting here. What we've learned is that e to the at times a and a times e to the at are in fact the same thing. And you can easily verify this using the definition of exponential. Okay. Now, the reason I point this out to you is that in general, if I have two matrices, A and B, two square matrices A and B, and I multiply A times B, and I compare it with B times A, okay, usually the two are not the same. Okay, usually they're different. So order matters when you're multiplying matrices. Okay, but in this case, the matrix A and the matrix e to the at, order doesn't matter. Okay. Okay, so now good. We know this is a solution. Okay, so great. So we have a solution. But the solution is what? An infinite series. Okay, so infinite series, not very useful. Not very useful. So third question, is there a better way? How can e to the at be evaluated? Okay, do we need a computer to approximately calculate these infinite series up to 100 terms or 200 terms? No. Okay. And there are several ways to find closed form formulas for e to the at. Okay, let me just show you one. Okay. Okay. So sometimes if you just write out the series if you're given some a, you write out the series. Sometimes you can see closed form solutions. Okay, like for example, cosines and sines will appear. Okay, if that doesn't work, one way to do this is if a is equal to p times d times p inverse. Okay. So some of you probably took linear algebra, okay, and you spent a great deal of time studying diagonalization of matrices. Okay. And some of you might have wondered, well, what good is this? Where can I use this? Okay, so here's a great place where you can use this. Okay. Now, so if A can be written in the form P times D times P inverse, okay, where D is diagonal, we'll get back to that later, then e to the at, okay, write out the series, is I plus, right, A, which is PDP inverse, times T, okay, next term, plus A squared, so PD P inverse times PD P inverse, T squared over 2 factorial, okay, plus dot, dot, dot. Okay, so what you notice here is that P inverse, P cancel. Okay, they cancel. You have D times D, D squared in the middle. Okay, so this becomes I plus P dP inverse plus P times D squared P inverse T squared over 2 factorial plus dot, dot, dot. Okay, so this, I can now pull out a P to the front, pull out a P to the back. So here's a P at the front. Here's a P inverse at the back. Okay, now this can be written I plus D times T plus D squared T squared over 2 factorial plus, okay. So this is what? This is just the exponential of d, of dt. So this is just p times e to the dt times p inverse. Okay? So this is true for any d, as long as a can be written that way. Okay? Now, if d is diagonal, okay, turns out that the exponential of dt is very easy to calculate. Okay, so e to the dt is just, well, let's see, it's I plus, then you have the diagonal matrix D. So let's say the elements are D1 up to Dn, zeros, times T, okay, plus diagonal matrix squared. Okay, so this is D1 squared, Dn squared, T squared over 2 factorial plus, okay, so on. So you notice that you get a diagonal matrix as a result. so this, in fact, turns out to be just e to the d1t, e to the dnt. Okay, so it's a diagonal matrix of just exponentials. Okay, so if you have a diagonal matrix, calculating the exponential is very easy. Okay, so if you have your a and you can diagonalize it, then calculating the exponential of a is quite simple. Okay. All right. So one more result we need. Okay. So one more result, and this one we're not going to prove. Okay. It's called the Cayley-Hamilton theorem. So, given some constant n by n matrix A, okay, it's characteristic polynomial. Okay, so if I ask you to find the eigenvalues and eigenvectors of A, first thing you would do, right, you would find its characteristic polynomial, P sub s. Okay, define this to be determinant of is minus a. Okay, you might have used lambda. Okay, you might have used I lambda minus a or a minus I lambda. Okay, doesn't matter. You can switch things around. No big deal. Okay, so this is the characteristic polynomial. Okay, and we know that its roots are the eigenvalues. Okay, so roots to PS equals 0. Okay, these are the eigenvalues. Okay, okay. So what the Cayley-Hamilton theorem says is the following. Okay, then. Now, if I replace S, the scalar S, by the matrix A, then Cayley-Hamilton theorem says this is equal to 0. Okay? Okay, so now you might look at this result and say that is the silliest result I've ever seen, right? Because you might say, well, if I replace S by A, that's I times A is A minus A is 0. Determinant of 0 is, of course, 0, right? And you say, this silly result has a name attached to it, right? But in fact, it's a little deeper than that. Okay? So what this means is that if the characteristic polynomial, okay, it's going to be a polynomial, right? Degree n. So Sn plus maybe C1 Sn minus, let's call it C n minus 1, Sn minus 1, plus dot 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 plus C1s plus C0. Okay, so if you calculate the characteristic polynomial and it looks like this, okay, then what Cayley-Hamilton says is that P sub A is A to the n plus Cn minus 1, A to the n minus 1, plus C1 times A, okay, plus C0. And now this is a matrix, so C is a scalar. Scalar times a matrix is a matrix. Kind of doesn't make sense to add a scalar to a matrix. Okay, so we have an I here. Okay, so what Cayley-Hamilton theorem says is that this is equal to 0, a 0 matrix. Okay. Okay, so we went over some tools from linear differential equations, okay, namely the solution can be written as a matrix exponential. Okay, we saw the Cayley-Hamilton theorem. Okay, next class we're going to use these tools and come up with a new representation for rotations. Okay, thank you.